All right, so where we had left off last Wednesday was on this problem where our goal is to determine AF ideal and K our feedback parameter. And then from that, we are hoping to be able to determine KA or our loop gain for our system, okay? So I identified my input signal VI and my feedback signal VF here. Now, because we are trying to find our ideal gain with feedback, that means that we need to set our input signal VI to 0, because the whole point of an ideal system is that our feedback is established entirely because of our gain is established entirely because of our feedback system with no contribution from our input signal. So that means in an ideal case, VI should be 0. And if VI is 0, VGS for transistor M1 is 0, right? If VGS for transistor M1 is 0, what amount of small signal current is our transistor going to carry? 0. So we can say that this current right here is 0 amps. And we did a little bit of algebra at the end of the last class, and I had a very, very small panic attack type thing. Effectively, in my notes, that fraction is upside down, and I wanted to make sure which one is right. This one that we have written down here is correct. So to determine K, this is simply the ratio of our output voltage, V naught, divided by our feedback, VF, feedback signal VF. So how we are going to determine this is effectively by looking at this guy and seeing what happens, okay? So V naught is the voltage drop over this resistor RF plus the voltage drop over this resistor RS1, right? We can use simple voltage division because we know that there's no current contribution coming in from the transistor in the ideal case where our input signal is 0, which means V naught over VF is simply RS1 over these two resistors in series. So RS1 over RS1 plus RF. From this, our ideal gain with feedback is 1 over K which is going to look like 1 plus RF over RS1. So based entirely on our feedback, we have behavior similar to that of a non-inverting op-amp, right? Where we are making a pretty large assumption here that our open loop gain of our cascaded common source amplifiers is actually infinitely large, which is very, very likely not to be the case. Okay. But we've stumbled into a way to figure out what our feedback parameter is using this assumption. So from here, we have determined our quantities for part A. We now need to figure out what our loop gain is, okay? So to do that, we're going to do the exact same thing that we've done previously. We are going to break our feedback loop, apply a test source, and measure what our return signal is, and then the ratio of those two things should be our loop gain. So let me erase this little algebra here that we used to make sure we were getting the right result. So here is what I have is RD1. Here's VS. This was RS1. And then in my original picture, just to make sure, I believe I just had a line, yeah. Here's M2, M1. This was RD2. Here's our feedback portion. Okay. So, and here's VDD. Those two guys together. All right. So, in order to determine our loop gain, what we need to do is set our source signal to 0. So I'm going to ground this guy out. And then we break our feedback loop. So I'm going to choose to break it here. So this is our return voltage, and then here is where we're going to apply our test voltage. And the reason why I'm choosing to break the feedback loop here is because this is the easiest place that I can find in the circuit, which should satisfy our criterion of not changing our open loop gain while also not changing whether or not our feedback loop is loading our circuit. Okay. So let's talk our way through what's going to happen. All right, oops, let's scroll a little bit. Okay. So if we apply some small signal test voltage, VT, to the gate of transistor M2, we should generate some small signal drain current, which I'm going to call ID2, flowing here, right? Now this current ID2, our ultimate goal here is to figure out what this return voltage is, okay? So this current ID2 effectively is going to split. Some portion of it is going to flow through RD2, and some portion of it is going to flow down through this potential path. And the portion that flows down through this potential path, some portion of that is going to be flowing through transistor ID1, which tells us effectively what our voltage VR is that we're looking for. So let's call this current right here IX, and let's call this current flowing up like so ID1, and start working on some relationships, okay? So, for example, one of the first things that we can hopefully see is that ID2 is simply GM2 times our test voltage VT. Are we all relatively okay with that? Another thing that we can hopefully easily see is that our return voltage, VR, is simply ID1 times RD1. The voltage drop with, from here with respect to ground is just the voltage drop over RD1 when this is an AC ground. All right. So the question then becomes, how do we take into account what's going on in the feedback portion? Right? So I am going to argue that we can use the concept of current division twice to figure out what's going on. Okay. So IX, for instance, I'm going to give myself some room down here at the bottom. Is going to be negative ID2. And the reason we're using a negative sign is because the current's flowing in the opposite direction as we want it to figure out how it's going to split up. And then we see two different paths. Okay. We have a path flowing up, RD2, which is the one we don't want. And then we have a path flowing to the right through the resistor RF, which is the path that we do want. Okay. But we do also have to take into account that this resistor RF, once we get past this point, our current has two distinct paths to ground. One going down through RS1 and one going up into the source of transistor M1. Since we're neglecting the effects of channel length modulation, what should that path up through the source of M1 look like? 1 over GM1. Okay, so ID2, and since we only have two paths, I'm going to use the current division relationship for only two resistors in parallel, where it's the path you don't want divided by the sum of the two paths. So that's going to look like RD2 divided by RD2 plus RF plus RS1 in parallel with 1 over GM1. That's giving us IX. Are we okay with that? So one path is just simply from this node to our AC ground through RD2. The other path to the ground is through RF, and then we have an option, of going down through RS1 or up through 1 over GM1. And so that is what I have reflected. Right. Now, IX obviously splits between RS1 and this 1 over GM1. So a second application of current division tells us that ID1 is IX times RS1 over RS1 plus 1 over GM1. Or we could write this as IX times GM1 RS1 over 1 plus GM1 RS1. And we now have a way, simply substituting IX into here, ID2 into here, we can relate the quantities VR and VT. Their ratio, again, gives us our loop gain, right? So VR is equal to ID1 which is IX, which is, let's see, ID2. So I'm going to have negative GM2 VT times RD2 over RD2 plus RF plus RS1 in parallel with 1 over GM1 times excuse me, GM1 RS1 over 1 plus GM1 RS1. So all of this stuff right here is just, sorry, let me double check that I'm doing this right. So trying to do all the substitutions in one go, and I'm trying to make sure that my brain is wrapping around this. So I have negative ID2 times RD2 over all of this stuff, which makes ID1, this bit right here. Okay, so I'm missing an RD1. So from this, our loop gain KA, which is defined to be negative VR over VT, looks like GM1 RD1 times GM2 RD2 times a factor of 1 over 1 plus GM1 RS1 times RS1 over RD2 plus RF plus RS1 in parallel with 1 over GM1. And I wrote it that way specifically because it stands to reason here, this GM1 RD1 and this GM2 RD2, that just represents the gain of both of the stages that were cascoded together. All of this stuff over here then represents the actual feedback parameter of the system when we aren't simply treating it as an ideal amplifier. Okay. So it allowed us to figure out what our real feedback contribution is as well. All right, so this was us determining our loop gain and all that kind of good stuff for this guy. Now what I would like to talk about is specifically the good reasons why we employ negative feedback specifically. And I just put the wrong notes on the wrong page. All right. So during our discussion about the pros and cons of positive feedback and negative feedback, I introduced a list, I believe, of 5 advantages of using negative feedback. They were gain desensitivity, noise reduction, bandwidth extension, the modification of input and output impedances, and improved linearity. Okay. Today, I hope to get through 4 of those, everything except for input-output impedance modification, because that's going to be a big part of what we're going to talk about next. And that modification depends very much on whether or not our feedback system is connected in series to our source or in parallel to our source, which in turn depends on what type of signal that we're trying to actually monitor. So that's effectively what we're going to spend the rest of the class on after today, is characterizing different types of feedback amplifiers depending on how we connect our feedback system. All right, so let's talk about gain stabilization. So when we looked briefly at positive feedback amplifiers last Wednesday, we observed that a small change in open loop gain A resulted in a very large change in the closed loop gain AF, right? So we worked an example where we had an open loop gain of 10 and a feedback factor of 0.0999. And we observed a closed loop gain of, I believe, 10,000 in that case. When we dropped our open loop gain by 1%, we observed a 90% decrease in our closed loop gain, right? So for a positive feedback system, we had a high sensitivity to changes in our open loop. Well, what we should observe for negative feedback is the opposite. A small change in the a small change in the open loop gain should cause an even smaller change in the closed loop gain. So let's say that I have a system where the open loop gain is 10 to the 4, and our feedback parameter K is 0.01. Our closed loop gain AF, and I'm going to call this AF1 because we're going to do another example in a moment, is given by A over 1 plus K A in a negative feedback system, which would look like 10 to the 4 divided by 1 plus 0.01 times 10 to the 4, or 99.010. So observe very easily here that the application of negative feedback serves to reduce the system gain for the closed loop gain. What if we have an open loop amplifier whose gain varies largely with operating point temperature, so that at a different temperature, it operates instead of at 10,000 at a gain of 9,000. Right? We would have 9,000 over 1 plus 0.01, excuse me, times 9,000, which comes out to be 98.901. So a change in the open loop gain of 10% resulted in a change in the closed loop gain of less than 1%. Actually, 0.1%, okay? So we're seeing that we get the exact opposite as what we experience with our positive feedback system. We have much, much more gain stabilization. Okay? Now, we can approach problems like this in this method, but there is actually a little bit better way that involves a teeny tiny bit of calculus. Okay? So what I'm going to suggest that we do is mathematically describe this phenomenon using a derivative. Okay? So what I want us to do is take the derivative of our gain with feedback with respect to our open loop gain. This would be the derivative with respect to our open loop gain of A over 1 plus KA. We can use the quotient rule to do this pretty easily, right? So using the quotient rule, I believe it is the denominator multiplied by the derivative of the numerator minus the numerator multiplied by the derivative of the denominator over the denominator squared, right? So that's going to look like 1 plus KA times 1 minus the derivative of the denominator with respect to A, so that's just K times A divided by the denominator squared. Comes out to be simply 1 over one plus KA squared. We're going to play around with this relationship here. Okay. So the change in the closed loop gain, DAF, is simply dA, the change in the open loop gain multiplied by this factor. So I'm going to explore that really briefly here, right? So I'm going to have a dA, and then I'm going to have 1 over 1 plus KA times another factor of 1 over 1 plus KA. Now what I'm going to do is I'm going to multiply my right-hand side by the open loop gain over the open loop gain, so that I have this. Okay. Well, this guy right here in the middle is just our closed loop gain, right? So if I move that term to the left-hand side, what I get is DAF divided by AF is equal to 1 over 1 plus KA times dA over A. And this is a handy little thing here. Let me explain exactly what I mean by that. On the left-hand side, DAF over AF represents the fractional change in the closed loop gain, or the percent change in the closed loop gain is another way to think of it. dA over A is the fractional or percent change in the open loop gain. So this statement says that the fractional change in the closed loop gain is simply the fractional change in the open loop gain divided by a factor of 1 plus KA. So this guy right here represents our gain desensitivity, because it tells us exactly how much smaller our change in closed loop gain will be due to a corresponding change in our open loop. So let's work an example. We could actually just throw this in with the numbers that we used a moment ago and see that they match perfectly. But let's see what happens when we look at something like this. So an amplifier with an open loop gain of A is equal to 1,000. Exhibits a gain change of 5% as the operating temperature changes from 25 degrees Celsius to 75 degrees Celsius. If we need to constrain the change, to 0.1% using negative feedback, what is the largest closed loop gain we can achieve? Effectively, we're looking at the trade-off that's going to occur. Right? If we use negative feedback to force our system gain to only be allowed to change by 0.1%, what is that going to do to the gain of the system? Right? It's obviously going to be less than 1,000, but by how much? What trade-off do we have to make in order to get this type of sensitivity? Right? So our fractional change in closed loop gain is 0.1%. This is the same as 1 over 1 plus Ka multiplied by our fractional change in the open loop gain, which is 5%. So rearranging this, we can find that our amount of feedback, 1 plus Ka, is simply 5% over 0.1%, or 50. And from this, our gain with feedback, or closed loop gain, A over 1 plus Ka becomes 1,000 over 50. So that constraint on our how much we allow our system gain to change has lowered our system gain by a factor of 50. Okay. So we have a much more temperature stable amplifier, but it cannot achieve the large gain that we observed in an open loop configuration. All right, so One thing that I'd like to point out regarding this equation is that since it's based on a derivative relationship, it's only valid for small changes in A. Now, the statement is definitely true, but the way that this behaves is a little odd. The lower our loop gain is, the larger the range of values this is valid. I was playing around with this yesterday when I was working on my notes. So when I had a loop gain on the order of tens, a 90% change, still the math worked out to be the same using this method or the direct method. When my loop gain was very, very large, say on the order of 10,000 or so, after about 20%, the numbers diverge pretty wildly. Okay, so use this equation with a grain of salt. I would say that 20% change is probably the maximum that you can comfortably do for most values of loop gain. All right. So let's look at the second example where we have a relatively large change, okay, and have to use the more direct approach. So I'm going to draw a signal flow diagram for a system. Okay. Here's our input signal, X of S. Here is our mixer. And I'm going to say that we have a preamplifier that is stable, feeding a power amplifier that is relatively unstable, meaning its output experiences pretty drastic changes depending on what its operating conditions are. And we are going to look at how we can use feedback in a system like this. Okay. So let's say that A power, the gain of a power amp portion of this system, ranges from 2 to 12, depending on how it's biased. Our goal is to have a gain with feedback of 100 plus or minus 5%. 95 to 105. And what we need to determine is the gain of the preamp and the feedback factor that must be applied in order to meet this constraint. All right. So because our gain of our power amplifier is experiencing up to a 600% change, I'm going to go ahead and say that this is too large to use our derivative-based relationship. 600% change, we can all agree, is a fairly large change. So what should our feedback, or excuse me, our gain with feedback look like for this system? Let's start there. Luke. Exactly right. So somebody who has had controls before, which I have not, is coming up with the same number as I am, so that makes me happy. You're probably bored to tears with all this easy crap. What? Okay, well, wonderful. So by inspection, our gain with feedback, according to Mr. Roger and myself, is A pre times A power over 1 plus K A pre times A power. So effectively behaves exactly like we would expect the feedback system to do, where we're just lumping together these two open loop gains or multiplying them together to get the overall open loop gain of our system, much like we treated cascaded amplifiers in circuits 2. So from this relationship, I can say that 105, our maximum closed loop gain, occurs when our power amp gain is at its maximum. So that'd be 12 times A pre over 1 plus K times 12 A pre. Our minimum closed loop gain of 95 occurs when our power amplifier is at its minimum gain, twice A pre over 1 plus K times twice A pre. So what I'm going to do now is I'm going to take the ratio of these two things. And what that's going to allow me to do is calculate Ka pre. And from there, I can calculate K and A pre individually, depending on the constraints of our system. So 105 over 95 is going to be equal to 12 A pre over 1 plus K times 12 A pre over 2 A pre over 1 plus K times 2 A pre. Since I'm dividing a fraction by another fraction, that's the same as me multiplying this numerator fraction by the reciprocal of the denominator fraction. So that's going to be 12 A pre over 1 plus K 12 A pre multiplied by 1 plus K 2 A pre over 2 A pre, which just looks like 6 times 1 plus 2 Ka pre over 1 plus 12 Ka pre. And so effectively, I have a one equation, one unknown system that allows me to calculate my loop gain, right? So I can just lump Ka pre together as a single unknown quantity. Solving for Ka pre yields 3.875. So this is what our loop gain is. And I can then substitute this relationship back in to either of these two closed loop gain expressions, which should allow me to solve for the preamp gain by itself. So we could say that 105 is equal to 12 A pre over 1 plus 12 times Ka pre, 3.875, which tells us that our preamp gain has to be about 415.625. And then from here, our feedback factor to achieve this variance is Ka pre over A pre, which comes out to 9.323 times 10 to the minus 3. So just to summarize what happened here, okay? We have a preamp gain and we have a power amp gain, so that we have a total system gain somewhere in the ballpark of 800 to 2400. If we want to constrain it to be 100 plus or minus 5%, we need to apply a feedback factor that's around 1 over 100. All right, so I think we have covered gain stabilization or gain desensitivity. You guys have at least an idea of what it is that I'm talking about when I bring it up. Okay? So effectively, negative feedback serves to if there is a decrease in the, or if there is a change in the open loop gain of the system, negative feedback makes the change in the closed loop gain of the system even smaller, meaning that generally speaking, our gains are more stable. Something that's a little interesting here, our feedback in these gain stability negative feedback schemes is usually applied using resistors. Does the resistance of a resistor change as a function of temperature? Absolutely, right? But what we wind up doing is using effectively what are called voltage divider networks. I mean, you guys are all familiar with that, where we effectively just have two resistors in series forming our feedback system. The reason why that works is because if we have two resistors in a network that are made out of the same material, they're going to both experience the same change in resistance due to temperature variations. So the ratio remains constant while the individual resistor values can go up or down with temperature fluctuations. Right? So that's how we're able to achieve this type of stability using resistors that are inherently unstable or are inherently dependent on things like temperature and process variation actually as well. All right. Now let's talk about noise reduction. So let's say that we have an amplifier circuit that is inherently noisy, okay? Let's look at an open loop configuration first. So how we might represent this, something like this, where we have our amplifier A, and then here is our output signal, Y, and the input to the amplifier is our desired signal, XS. And then also this signal, which we're going to call X noise. Where X noise in this case is what I'm going to call the input referred noise. So all input referred noise means is that if I have a very noisy amplifier, like what you ladies experienced in the lab the other day, a very noisy amplifier, you see the noise at the output of the system. Well, the input referred noise is simply that noise at the output divided by the gain. So we make it appear as if it's occurring at the input so that we can do a direct comparison between the input referred noise level and our signal level, because we need to compare those two things at the input to determine whether or not we can actually see our quantity of interest, which is quantified by a signal to noise ratio. Okay, so in this case, our output Y would simply be A times XS plus noise, meaning that both our input signal XS and our input referred noise, X noise, are being scaled by the same amount. So they're both being amplified by the same scaling factor, okay? So if we were trying to look at, let's say, the power that's delivered to an arbitrary load resistance by this signal, we could break it down into two contributions. A signal power, so this is the part that we want, which would look like A XS quantity squared over RL, and then a noise power, which would look like A X noise quantity squared over RL. Where in this case, we're assuming that our signal and noise quantities are voltages, but this would work just as easily if the signal and noise quantities were currents. Okay. Our signal to noise ratio, or our figure of merit for our amplifier here when doing any sort of noise analysis, is defined as the ratio of P sig to P noise, which in this case is going to simplify to XS squared over X noise squared, meaning that the open loop gain of the system doesn't matter. The load resistance that we're delivering power to doesn't matter. It's simply a ratio of the signal strength, a square of the signal strength to the square of the noise strength, right? In decibels, which is how this is more frequently expressed, the signal to noise ratio is given by 10 times the log of the regular signal to noise ratio, which just comes out to be 20 log XS over X noise. So let's see what negative feedback can do to the noise behavior of a system. All right. So let's look at something similar to our last example problem. So we have our signal of interest, XS, and it's going to be fed into a preamp. I'm just going to call this A2. The output of A2 gets mixed together with our noise signal, which in turn gets sent to amplifier A1, our noisy amplifier. Okay. Here's our output Y. Here's our feedback network. Okay. I'm going to call this X2. I'm going to call this X1. I'm going to call this X2. So what we're going to do here is we're going to figure out what our relationships are so that we can calculate our new signal to noise ratio. The assumption here that we're making is that amplifier A1 is much more noisy than amplifier A2, which is pretty typical for something like an audio amplifier, where the preamp, its goal is to give you a very, very nice boosted signal. And then the power amplifier really depends on how well, or the performance of the power amplifier really depends on how well things like grounding and all that kind of stuff are handled. So like for you guys that do a senior design project based on some type of audio amplifier, I would beg you not to test it upstairs in the circuits lab, where 60 hertz hum is going to be coupled to effectively any and everything you could do, which is what has happened in numerous other senior design projects here, because this building is not grounded particularly well. So let's look at what we've got going on here, okay? Our quantity X2. Sorry, since this is a negative feedback system, our quantity X2 is simply the difference of XS and XF, right? According to our signal flow diagram here. Well, XF is K times Y. So this is going to look like XS minus KY. X1 is going to be A2 times X2 plus X noise and Y, our output, is simply A1 times X1. Does this describe our signal flow diagram appropriately? All right. So now we're simply going to substitute in our relationships. And we should see that Y is equal to A1 times A2 times XS minus KY plus X noise. And with a little bit of algebra, this becomes XS times A1, A2 over 1 plus K A1, A2 plus X noise times A1 over 1 plus KA1, A2. So what has happened here due to the application of negative feedback? So when we had our open loop system, our signal and our noise were scaled by the same amount. In this closed loop system with negative feedback, our signal is scaled by a factor that is A2 times larger than what our noise is scaled by. meaning that our signal to noise ratio is boosted by a factor of A2. This is how negative feedback is utilized to increase the noise performance of a system. We got here at 1:45, right? Yeah. Okay, I'm not going to do that example problem. Now let's talk about bandwidth extension. So let's say that we have an open loop amplifier that has a one pole transfer function. So A as a function of S is given by the midband gain divided by 1 plus S over omega high. Okay. So graphically, this would look something like this. So this is our gain. Here's AM. Then at omega high, it should fall off at a rate of roughly negative 20 dB per decade. Okay. If we were to apply negative feedback using a feedback network whose K value is independent of frequency, so like resistors, we would find that our closed loop gain, A F of S, would look like AM over 1 plus S over omega high divided by 1 plus K times AM over 1 plus S over omega high. And so what I'm going to do now is I'm going to multiply through by a factor of 1 plus S over omega high over 1 plus S over omega high. And this will give me AM divided by 1 plus KAM plus S over omega high. Well, now what I'm going to do is I'm going to multiply by a factor of 1 plus KAM over 1 plus KAM. And what this gives me is AM over 1 plus KAM divided by 1 plus S divided by omega high times a factor of 1 plus KAM. So what this means is that our closed loop gain now becomes AM over 1 plus K AM, but our closed loop bandwidth is now omega high multiplied by a factor of 1 plus K. So effectively, lowering our gain by a factor of the amount of feedback boosts our bandwidth by a factor of the amount of feedback. It's why the gain bandwidth product of a negative feedback amplifier is constant. So this should be something that you all have observed previously. All right, going to skip another example problem so I can finish up what I wanted to talk about today. That last thing is linearity improvement, and then we're done. And this is going to be pretty short and straightforward. It's going back to some things that we talked about in circuits 2. Okay, so tuck it in right here. Let's say that I have an amplifier whose transfer function looks something like this. Okay. So here's my output voltage, V out. Here's my input voltage, V in. And let's do this in red. Trying to do is draw something approaching a straight line here. Something like this, okay? Where the output of our amplifier is constrained by our power supply voltage, right? And the slope of this guy is our open loop gain. Well, the linear range over which this amplifier circuit is able to actually amplify a signal is very small, right? We define this back in circuits 2 as simply Vn would be less than or equal to A over VCC minus to less than or equal to A over VCC plus. So that's our linear range, right? So if we have an amplifier with an open loop gain of, let's say, 1,000, and we are going to constrain the output of the amplifier to supply voltages of plus or minus 10 volts. And that means that our linear range extends to like negative 10 millivolts to positive 10 millivolts, which for the overwhelming majority of applications isn't particularly useful unless we know that we're going to be trying to amplify signals of that rough scale, right? Well, if we apply negative feedback, what are we doing to this graph? Spreading it out. Okay. So that we might see something more in line with this. By applying negative feedback, we can greatly increase the linear range over which our amplifier can actually work. That's it. That's pretty simple and straightforward. We actually kind of covered that in circuits too. All right, so we have 2 to 3 minutes, so I'd like to talk to you very, very briefly about your next exam. My goal, because I seem to be incapable of writing problems that you guys can actually solve in a reasonable amount of time, is to give you yet another take-home test for exam 3. Is that right? The goal here is to give you this exam Friday or this weekend and have you turn it in on the last Friday of classes. Does that sound unreasonable? Yes. So for you, because you're a graduating senior, I have to think of something to do for you. Pardon? Oh, well then why do you care? No, we totally are. Yeah. So you don't just get like we're not going to not have class next week. There will be material that we are covering next week that will show up on your exam. So that it's going to be in your best interest to work on some of this. It's going to be in your best interest to not procrastinate and to kind of do the problems as we cover the material. So there's going to be a couple of problems. Like I'm very likely, I'm trying to decide whether or not to give you the example problems that I skipped as just homework problems because I already have the solutions and all that kind of crap. So I don't have to wait to give you numerical responses and all that kind of stuff. Part of me wants your take-home test to be one voltage amplifier. So one problem for a voltage amplifier, one problem for a transconductance amplifier, one problem for a transresistance amplifier, and one problem for a current amplifier, which is what we're going to be spending the next several days talking about. And then part of me, because that's largely what the feedback stuff is all about, and then part of me wants to incorporate some of this stuff that we've talked about as well. I am just unsure of what to do to give you guys the best opportunity to do well in the limited amount of time that we have, because I don't want to bog you down with a homework and an exam just for the sake of giving you homework. Does that make sense? So I'm absolutely open to suggestions. That is a very reasonable thing, actually. That may be the way to do it. Would anybody object to that? Me giving you guys, like, let's say 5 to 6 problems and you doing roughly 2/3 of them? Okay, I think that's a fair way to approach it. Any questions, comments, concerns regarding the upcoming exam? Yeah, I'll work on one homework set and I'll try. So my goal for tomorrow is to actually start grading you guys' exam once. Yeah. Yeah. If I'm able to keep myself awake tonight, I'll work on getting a homework set going. That effectively will be one homework set. It's probably going to be kind of long, that literally covers all of this stuff, like everything that we've covered to this point and everything we're going to cover over the next several meetings. So potentially 6 to 7 problems. But yeah, but it's all gonna be due effectively the same day as your test, which that's another problem. You're having a homework set due the same damn day as your test.
What if you just gave us some of what said and we do it when it's done? So that would be practice, but we don't have to be like, but it's, you know, they're still gonna do it. I just don't wanna, I don't wanna be stressed.
I feel like
about-
prep the homework's looking nice.
Yeah, I will definitely take that under consideration, because I've done something similar to that in previous classes, like when I was a grad student. And I taught the linear systems and signal course and the digital signal processing course. I gave homeworks explicitly telling them I had no intention of actually taking it up or anything like that. It was just practice problems to show. Yeah, I'm thinking that that's what I'm going to lean towards. Because I can give you my solutions, you'll have something to work towards. So having it too close to your exam, I guess, isn't wildly unreasonable when I have a means by which for you to check your work kind of built in. So I think that's probably the way. Okay, I'm going to stop talking before I talk myself into or out of something dumb and say that that's what I'm going to do. And yeah, submission portal for the current exam. Send me an email and I'll go do it. Yeah, I'll go do that. All right, thank you guys. See you on. That's what they literally just asked about, and the yes, yes, I will.